This meeting is being recorded.
شكرا. السلام عليكم. أحب نبدأ بشكر الجمعية العربية للفيزياء وخاصة الدكتور شعبان خليل على الدعوة. أنا ممتن كثيرا لهذه الدعوة ويشرفني أن نقدم هذه المحاضرة وهذا الدرس اليوم. So now I'm going to switch to English first by sharing my presentation. So can you please allow me share my presentation? I need some permission from your side.
لحظة واحدة يا دكتور، احنا بس
شكرا.
نشيل الاكونت.
Okay. So can you see me? في صوت مزعج في الرجوع يا دكتور. So can you see the presentation now, please?
Yes, we can see the presentation. Doctor, can you start the record? I think it started, didn't it?
It should be started. Should I start it myself, or you can do that?
No, it started. So
Okay,
you can
thank
start.
you.
Thank you.
Thank you. So thank you once again for allowing me to give this presentation here in this second summer school on advanced physics organized by the Arab Physical Society. I'm sending you greetings from Tunisia, for all the attendees, for the organizing committee, and especially for Dr. Sha'ban Khalil, who gave me this opportunity. So my lecture actually is the second in a series of 3 lectures devoted to nuclear fusion and its applications. You started yesterday with Dr. Ayman al-Batayna with a lecture on nuclear physics and nuclear fusion. Tomorrow you will have more details about a specific device, which is ITER fusion device in France. And today I will present a specific problem related to this very interesting physics of magnetically confined plasma for fusion. So the outline of my lecture is as follows: brief introduction, where I will review the main things you have seen yesterday. Then I will move to the heart of the presentation about atomic and molecular physics and the processes and a part of the fusion device called the edge region. Then I will present some theoretical models to study this important problem before moving to some more specific details about spectroscopy and accuracy and so on, and then conclude. So I guess all of the attendees are now familiar with nuclear fusion after the lecture of yesterday. So basically, two light nuclei, the mostly used for fusion are tritium and deuterium, two isotopes of hydrogen. So they fuse under certain conditions of very high temperature, density, to give as products an alpha particle or helium nuclei plus a neutron. So if this reaction can take place and can be sustained, it can produce energy as the products will have important kinetic energies of the order of magnitude is the mega electron volts or 10 mega electron volts. The neutrons will be later on absorbed by some material, heated, and this heat can be converted to steam and then produce electricity. This is the goal, while the helium nuclei of alpha particle can be recycled or trapped in a specific part of the fusion device. So why nuclear fusion is so important? Actually, it was a kind of a dream, the dream of producing almost limitless energy, since the main fuel components, which are tritium and deuterium, are available in very large quantities all over the world. It's not like for fission where you need uranium, and uranium is not available for everyone, and then you have to enrich it, and this is very costly and requires very advanced technologies every countries can't afford. The next point is very important also from the environmental point of view, as this technology is environment friendly, no greenhouse gas emissions. Another very important point concerns the possible accidents. You know that nuclear technology is quite risky, and we have had during the last decade some big accidents with nuclear reactors based on fission, of course. The last one on Fukushima was on the news, and I think all the attendees are aware of that. So here in fusion, there is no such risk due to meltdowns or explosions, because the fusion mechanism can be shut down at any moment very rapidly and safely. Also, one of the big issues of fission technology is the production of dangerous and with long half-lives radioactive elements. This is no more the case with fusion. Light elements like tritium and maybe a few others have very short half-lives and are produced in small quantities, so there is really no risk, almost no risks. There is no zero risk, of course, but the risks are very limited. The other point, the last one, concerns proliferation and safeguards. As you know, nuclear fission can be also used for weapons and so on. The fusion also can be used in principle to produce like a hydrogen bomb, but it's very unlikely because it requires in most of the cases a fission-based device on the same bomb. So with only a fusion devices, the proliferation risk is very limited. Okay, so good. So now how to implement in the real world the nuclear fusion? Many ideas. The two main technologies used or under development today are the inertial confinement fusion and the magnetic confinement fusion. In the inertial confinement fusion, as you can see on the left side of the slide, in this picture, So here in the center, you are supposed to have a very small pellet containing deuterium and tritium, the dimension of which is like millimeters, on which, in the case of the National Ignition Facility in USA, about 200 lasers, to be more specific, 192 extremely powerful lasers are focused and heat the pellet and produce enough high temperature to start the ignition and the fusion reaction. So this was already achieved. Actually, it was on the news about 2 years ago. You may remember that in December 2022, big announcement by the Department of Energy of USA announcing that for the first time ignition was reached, which means that the amount of energy produced by the fusion reaction was larger than the input energy. And so this was really a big breakthrough. But still a lot of challenges are continuing to be addressed by people in Livermore and other places in the world to make it sustainable and to be able to produce energy with it. The second technology to implement fusion is using plasmas confined magnetically. So a plasma, to be very simple and very brief, is mainly a state of matter where all the atoms and molecules are ionized. So you have almost only, in the ideal case of 100% ionized plasma, only electrons and ions, atomic or molecular ions. So these are charged particles, and charged particles are sensitive to electric and magnetic field. So with a suitable geometry, like here on the right side of the picture, as you can see in this cartoon, a toroidal device called the tokamak with magnetic field produced by the specific coils can confine and guide the plasma inside this device. And then the plasma can be heated up to very high temperatures exceeding 100 million degrees, so that at these relatively low densities, fusion can occur in this hot plasma. The main device under construction, there are many all over the world, but one of the most important ones is in the south of France. It is called ITER. And tomorrow, in the lecture by Dr. Amro Badr, you will learn more about this project and the technology aspects of it. So today I will more speak about some fundamental aspects regarding specifically a part of the fusion device or of the plasma. So here, if you like, it's a cartoon of the one of the components here of the tokamak, as you can see. You can see some people here, so to have an idea about the dimension, it's quite large. And if the plasma is heated enough and the fusion reaction starts, you will have here mainly two different regions in the tokamak. The core region, the very hot region, as I said, about 100 or 150 million degrees, where the deuterium-tritium fusion reaction takes place. In black here, you have the walls of the tokamak, which is cold part. typically.
What's the temperature?
And in between, you have the what we call the edge region, which separates the core region, the hot region, from the walls. And I would like to focus on this region and on the processes that can occur here. So this is the main point in this lecture. Are you hearing me, please? I'm getting some...
Yes, we can hear you, but
okay, thank you.
Some noise.
I'm getting back some noise from the room, but it's okay, it's fine. Okay, so I will focus on this region, the edge region, which includes the bottom here, which is very important because it is what is called the diverter region, where all the ash, all the unwanted products can be directed here and eliminated so that they do not contaminate the core region, which is ideally formed only by what is needed, the fuel, deuterium and tritium for the fusion. So this edge plasma region is very important for many points of view. First, it's, as I said, an interface between the hot burning plasma of deuterium and tritium and the cold material walls of the reactor vessel. This is the first point. So this region has to protect the tokamak walls from the intense particle and power flux generated inside the hot zone. And it has to secure and protect it also from contamination by impurities, because of course, when the very hot particles hit the wall, they can how to say, they can scratch it in some way, and some of the components of the wall can go into the central plasma, which is not good because it will diminish and lower its capabilities and performance. And the last point is that, as any reactor, there are always unwanted products to remove, like thermalized helium and some ash. And this is also the role of the edge region to do that. So now, another aspect concerning this region is that it is at low temperature. Of course, here low means, I mean, not room temperature, but temperature relatively low compared to the core region. In the core region, it is like 100 million degrees. In the edge region, it is, let's say, thousands, tens of thousands, or maybe hundreds of thousands of degrees. But still, these temperatures are low enough so that several processes can occur and form like some neutral atoms, like neutral hydrogen. So protons and electrons can recombine to form neutral hydrogen, and also some low charged atomic and molecular impurities produced, as I said, in the plasma wall interaction that may occur. So it is important to study these aspects, but the range of collisional processes involving the electrons and ions is extremely large, as we will see. So it's a really complex physics. At the same time, it is important to well describe them because these processes affect the plasma edge properties and behavior. So many aspects like the ionization balance, etc. So this is crucial for the sustainability of the fusion and of the plasma in the core region. So as a conclusion here, is an in-depth understanding of atomic and molecular processes in the edge plasma region is necessary for good and realistic modeling of the fusion physics and the device functioning. So it is very crucial to understand that. So this allows me to move to this, what are these processes? The most important among them, from the standpoint not of fundamental physics, not only from fundamental physics, but also from their effects on the plasma itself, are the electron impact excitation and ionization of atoms, ions, and molecules. So electron impact, electron-ion recombination, giving neutral products, dissociative processes. So this is possible only when the target is a molecule. So you have a molecular ion, let's say H2 plus, you hit it with an electron, and the products can be two neutral hydrogen atoms. And also another important effect is the electron capture by ions, either atomic or molecular ion, the capture of an electron. So as you can see here, the word electron is appearing every time, and we can summarize all these processes by saying like electron atom or electron molecule collisions. So the main atomic and molecular processes occurring in this edge plasma region are, their nature is electron target collisions. The target can be an atom, a molecule, in general light one like H2 plus, Hg plus, etc. And to be brief, because I do not have a lot of time here, I will more focus on the following, on electron molecule collisions, which is more complex than electron atom collisions. So my hope is if you understand the more complex process, it will be easier for you to understand the electron atom collisions. So if you take the example of ITER as a fusion device, the simulations show that at the energies and temperatures in the edge region, so from 0.1 to 200 electron volts, which can be converted in terms of temperatures, given the conversion factor, which is 1 eV, is equivalent to 11,600 kelvins. So say roughly 10,000 kelvins. So you can see here that this range of temperatures goes from like 1,000 or 2,000 degrees up to like 1 or 2 millions. With densities around 10 to the power 20 per cube meters, which is not very high, actually. We are still here speaking about a gaseous phase. Still, under these conditions, several neutral or ionic molecular systems are present, mostly H2, ground or excited, H2 plus, H3 plus, water molecule, carbon monoxide, carbon dioxide, methane, CH, C2, beryllium hydrides with the three main isotopes of hydrogen, so hydrogen, deuterium, and tritium, but also a lot of other products like oxides, nitrates, hydrocarbons, etc. These come from the reaction with the walls, and also other molecules containing mainly tungsten and beryllium, which are main components of the blankets of the walls inside the tokamak. So you see here how complex can be the study of all the interactions of these systems among themselves, and also the collisions of electrons on them and the products, to calculate the cross section, the rates, etc., to be able to have a good modeling of the plasma fusion device. We can note here probably this is more for specialized people, but still it is interesting to see that similar physics can occur at other important devices, which are the cryogenic storage, the storage rings in general. Specifically, the cryogenic storage rings is one of them in Germany, where the temperatures are more or less of the same order of magnitude or slightly higher, and where you can also find the part of the cations also present here, like Hg+, H3+, and so on. So it is possible to bridge the gap and to use the same, let's say, models, the same theories to understand both. And this allows actually for good collaboration between teams from these two different communities. So if we want, for instance, to study the electron-molecule collisions inside this plasma H region, we have to emphasize that actually it is more complex than electron-atom collisions for the following reasons. First, molecules are more complex systems, so they have more degrees of freedom. They can vibrate, rotate, and these vibrational and rotational degrees of freedom have to be taken into account, especially at very low collision energy. The second point is that molecules in general are, as you know, a molecule is formed at least by two nuclei. It can have much more, 2, 3, 4, and even higher numbers. So it is multi-centered and non-spherical. So the polarizability of the target is anisotropic because of the anisotropy of the system itself. And then you have to deal when treating theoretically the systems, not only with the dipole moments, but also with higher multiple moments. So all these aspects make the theoretical study of electron-molecule collisions much more difficult than the electron-atom collisions, which is also difficult. But here you have another layer or another level of difficulty to add. So a question now, what are these main electron-molecule collisional processes? And to make it as simple as possible, I'm taking here the case of a diatomic molecule, AB, with a colliding electron at relatively low energy. So what are the possible outcomes and the processes? The simplest one is scattering, elastic scattering. So typically nothing happens. The products are exactly in the same states as the reactants. At higher energy, you can excite the molecule, and part of the kinetic energy of the colliding electron goes to the molecular system in the form of excitation, either rotational excitation, vibrational excitation, or electronic excitation, and in general, a kind of mix of all of them. And in all cases, the electron, the colliding electron, is scattered and loses part of its kinetic energy. At even higher energies, dissociative processes play an important role. So the electron, the kinetic energy of the electron is high enough to dissociate the molecule, giving birth to an ion and a neutral, one or the other, or both neutrals. So this is the dissociative recombination of a cation. This is a particularly important process, as you will see later on. And the impact dissociation, which is uses like an intermediate state first electronic excitation. So to summarize all these processes, let's say there are two classes: excitation without dissociation. This is the first class of processes. The second one is dissociative. So the products are neutrals or neutral atoms or atomic ions. At the same time, what is common to all these processes, if I take the prototype case of H2 plus cation with an electron. So all these, these acronyms stand for dissociative recombination here, or dissociative excitation, a combination of impact dissociation and electronic excitation, or dissociative ionization. So all of these processes and others actually have in common that for a brief time, a neutral compound is formed. So first, the electron is captured by the cation, forming a neutral. Here in this case, A and B are simply protons. So you have the hydrogen molecule in excited state. So one electron is in the high orbit, we call that the Rydberg state, or a doubly excited state where both electrons are excited. So this means that to study these reactions, it is very important to have good understanding and description of these neutral intermediate compound, which can be very simple, like a hydrogen molecule. The issue here is that you need a good and unified description of all possible states of it, including very high Rydberg states. So how to do that? Several methods, theoretical methods exist, but they depend on the energy range. So the temperature or the kinetic energy of the electrons. This energy range can be roughly divided into three intervals: low energy, intermediate energy, and high energy. So the limit here is the ionization threshold. So if due to the impact by the electron, the molecular target is not ionized, you are in the low regime. Just above the threshold, this is the intermediate regime. If the energy is high enough to ionize, you are already in the high energy regime. So depending on the energy range, various options are available. Of course, you can think about why not only one. So actually, in physics, we proceed, as you know, little by little. In case we can use a simple method under certain circumstances, it's a good idea to use it. When it is no more valid, you improve the model and use a more complex theory. So it's not always a good idea to use the most complex theory to study a very simple problem. For instance, while studying in the textbooks of quantum mechanics, as you know, atomic hydrogen, you do not need from scratch directly. You can do that, of course, but you do not need full relativistic and quantum mechanics study based on Dirac equation or quantum field theory. Non-relativistic Schrödinger equation is a good starting point. But if you need more refined effects, of course, you can move to quantum electrodynamics and so on. So this is the main idea. When we deal with high energy physics, even very simple classical methods or with classical background methods like those based on Born approximation, perturbation theory, and so on, which are kind of light and can be used very efficiently, are recommended. However, this is no more the case at low energy collisions because the quantum properties of the system show up, and you have to take account of the photoionization processes, and also you have sharp resonances which appear, etc. So no classical methods or quasi-classical methods can help you here, and you absolutely need to start with quantum mechanics, even non-relativistic, based on Schrödinger equation, but still with this kind of system, you will see that it is not that simple. So this is what we call the ab initio methods. So just starting from scratch, building up a Hamiltonian, and then try to apply the tools of quantum mechanics to solve the problem. So the main theories used in these kind of problems are the Schwinger theory in the multi-channel case, complex cone variational method, and here in blue, R-matrix method with different versions. Of course, if you are not at all familiar with this field of research, this is just like a kind of vocabulary, and I apologize for that. We need more time to go into details, and maybe not everyone is interested in, but at least here you have these keywords, and if you are interested in more in-depth understanding of them, you can just take these as a starting point and go further. So why R-matrix method here in blue? Because it is my choice here to take one of the methods, the R-matrix method, and try to develop it a little bit during this lecture. What is important here, as we have seen a few slides before, is that while describing the compound, the neutral compound, highly excited states, which we call the Rydberg state, play an important role in the processes in the example of, dissociative recombination. So you need to use the best possible tools to study highly excited states and Rydberg states. So for this, there is a very good theoretical framework which is well adapted to Rydberg states, known as the quantum defect theory. Quantum defect theory. The basic idea is very simple. You know that from the textbooks, even on undergraduate lectures. When you consider an alkali like lithium or sodium or whatever, the energies are very similar to those of hydrogen atom, except that they are a little bit lower, and this amount of energy missing, this kind of defect, can be just described with a number named a quantum defect, and which can be tabulated and used for different applications. So this is the very simple case of an alkali atom. The same ideas are still valid for more complex systems, except for the fact that these quantum defects, given the multi-channel, as there are many possible channels of the reaction, became more complex. We deal with matrices of quantum defects, with diagonal and off-diagonal elements, but still the main idea is the same. So a good idea would be to combine this already available framework, the quantum defect theory in its multi-channel version, with the R-matrix method. This is the main idea. So historically, the what is called the R-matrix theory was originally invented in the 40s of the last century by Eugene Wigner and the collaborators in the context of nuclear collisions. So this can seem weird. Why nuclear collisions here, while we are speaking about collisions of an electron on, so more with atomic collisions and molecular collisions? Because all of these systems are actually, from the formal point of view, nothing but a scattering problem. So scattering particle, colliding particle, whatever it is, an electron, a proton, a nuclei, light or heavy, etc., is colliding on a target. So all this physics can have a kind of common core, and the same methods can be adapted from one discipline to another. For instance, here the R-matrix theory was indeed adapted by people like Burke. I'm giving here a snapshot of the very good book if you are interested in. And later on, more recently, like in the 80s, 20s, at the beginning of 2000 years, a very good code called UK, United Kingdom Armatrix code, was developed and was very successful in dealing with what is the problem here? Electron molecule collisions, so including even polyatomic systems. So this would be, in this kind of lecture, a good method to teach and to show how it works. However, in the following, I am a different choice, and I will speak about Armatrix, but in the version which is slightly different. It is very good for diatomic systems, and the advantage of the diatomic systems, especially here in summer school, that we can understand and follow step by step what is happening. The other reason is that I had the honor and the pleasure to contribute to the development of this part. So let's speak a little bit about this, what is called the Halford Armatrix method. So originally, the Eigen-channel Armatrix theory was developed for atoms, mainly by Chris Green and Mireille Hébard. Chris Green is now presently based in Purdue, US. Mireille Hébard and Le colleague from CNRS in Paris. And so you have here a review paper dealing with almost all what has been done with this method for alkaline earth atoms. So what we did with my collaborator Chris Green and Christian Jungen mainly here is that we adapted this kind of approach to diatomic molecules and developing an alternative code for the mainly for the molecular hydrogen. So let's start little by little with basics and consider standard non-relativistic electronic Hamiltonian for a molecule, diatomic molecule. Of course, within the Born-Oppenheimer approximation, so the two nuclei are fixed at some position, some geometry. So the Hamiltonian contains the kinetic energy here in atomic units. I remove the H bar and the masses, etc. So the kinetic energy of the electrons, I have n electrons, small n electrons here. The potential energy with its two components for the attractive part, the Coulomb attraction of each electron by nuclei with charge Ze and Zb. Okay, this is attractive, and the repulsion term, which describes the repulsion of each pair of electrons. Simply 1 over the distance between electrons I and J. So as you may know, this is the most difficult part to deal with. And what we do in general, we develop it on the basis of the Legendre polynomials as an infinite sum over all partial waves. L here stands for waves. L equals 0 is S wave, L equals 1 is P wave, then D wave, F wave, etc. And each term is proportional to Legendre polynomial with degree L and multiplied by this fraction. In the higher part, you have the smaller r at power L, and here in the denominator, you have the larger r at the power L plus 1. So with the smaller and larger, you have two, imagine that you have like for given pair of electrons, 1 and 2, like here, I and J, as these are undistinguishable particles, You cannot label them because of their quantum nature. So depending which one is closer to the nuclei, it can be one or two. In all cases, this is well known and used in all the methods of interaction configuration, Hartree-Fock methods, etc. If I go further in simplifying the problem and considering only one electron, so I'm considering here very simple system formed by two nuclei and one electron. An example of that is H2+, but it is not the only possible example. You can have any nuclei. So any charges ZA and ZB. So the Hamilton in this case is very simple. The kinetic energy is the one of only one electron, the electron of the system, attracted by both nuclei. And you don't have, of course, any interaction term here because you have only one electron, while you need at least two electrons to have this kind of terms. So how to study this system and how to solve this Hamiltonian or the Schrödinger equation? There are several methods. The one I would like to introduce here is that using a kind of specific coordinates, probably not very known or popular. The most known coordinate systems are, as you know, spherical coordinate system by far, but also cylindrical systems. Well, in atomic and molecular and nuclear physics, we do not use that much Cartesian coordinates, but there are other kinds of like perimetric and so on, hyperbolic, many possible coordinate system. One very good here and very suitable to the system, taking into account that we have like two singularities here, 2 points, which are different from all the other points of space, the positions of the two nuclei, separated by a bond length or internuclear distance r, given r. The typical range for r is a few atomic units or few angstroms. So if RA and RB stand for the distance of the electron here from each one of the two centers, we can define the sum and the difference divided by R as two new coordinates called prolate spheroidal coordinates, psi and eta. Psi and eta. So just the sum or the difference of these two distances divided by R. So to have an idea about the link with the spherical coordinates, if the electron is far enough, it goes very far here, of course, it will see more and more these 2 points coming closer. And the same happens if capital R goes to 0, of course. And in this case, xi is nothing but 2 small r divided by R. So if I forgot about here, about capital R here, which is a parameter, it is mainly the radial coordinate R. And in the same time, eta, the limit of theta, of eta, sorry, is cosine theta, where theta is the simple spherical angle. So here to see the geometric link between these new coordinates, prolate coordinates, and the more known spherical coordinate. The third coordinate is, of course, phi, the rotation angle around the z-axis, which is the same as in spherical coordinates. So the question now is why this coordinate system is good for our problem. First, we can write the Hamiltonian here in terms of psi and eta, okay? And then solve the Schrödinger stationary time-independent Schrödinger equation to find the spectrum, the energies, and the wave functions. The good news here is that thanks to the use of spheroidal coordinates, the wave function can be factorized as the product of radial function, an angular function, and phi function, which is simply exponent of I lambda phi, exactly like in an atomic case. So the good news here is the separability. So the main advantage of using spheroidal coordinates is to maintain a separability and to go back to the background picture we have always in mind when doing atomic and molecular physics, which is the hydrogen atom, the only and unique system for which we can use, we can solve exactly the non-relativistic Schrödinger equation. The only one, of course, hydrogenic ions also, but it is the same physics. A point charge, positive point charge, plus an electron. So following that, we can define almost the same quantum numbers you are used to, like the equivalent of the magnetic number. M here, it is lambda because the rotation is not like in hydrogen atom about any axis, but about a specific axis, which is the internuclear axis, but still it is exactly the same part of that. The value or the possible values are the integer values, positive or negative. Then the Schrödinger equation splits into a radial function and an angular function, which has the same form, like the second derivative plus a function that multiplies the wave function itself equals 0. If this is constant, this is nothing but the harmonic oscillator. And this is analytical, but it's not that complex. It's just a function of the coordinate. So easy to solve, of course. And we can check that in the limit of spherical coordinates when capital R goes to 0, we find exactly the same thing here. We need, of course, a separation constant, which turns out to be just minus L, the centrifugal term which appears in hydrogen atom, as you know from quantum mechanics textbooks. So this means that with this choice of coordinates, it is possible to solve exactly the one electron diatomic molecule problem. This is known as the two-center Coulomb problem. And define, in addition to lambda quantum number, the equivalent of azimuthal or magnetic quantum number, a kind of orbital or angular quantum number L, which starts at lambda plus 1, like for hydrogen atom, L equals m plus 1, etc. Except for here we are adding in the notation a kind of this tilde, indicating that this is not exactly an angular momentum because the angular momentum is not conserved in the system because of the breakdown or the loss of spherical symmetry. We do not have spherical symmetry here anymore. We have two singularities, 2 points, so at least an axis of symmetry. Okay, but when you solve the radial equations, as you can see here in this graph, what you find is very similar to the radial wave functions of a hydrogen atom. A nodeless function, then a function with one node, then one with 2 nodes, 3 nodes, 4 nodes, etc. And this allows you to define, like in a hydrogen atom, a kind of principal quantum number, which starts from L tilde plus 1, L tilde plus 2, etc. And which is here a good quantum number related to the number of nodes. So finally, here at this level, the one electron two-center problem is well mastered and can serve as a reliable ingredient, like for more complex molecules, like the hydrogen atom serve as an ingredient for the study of more complex atoms. And we can define quantum numbers NL and lambda to identify each eigenstate. So for instance, here for H2 plus, the ground state or the fundamental state notation is 1s sigma. 1 stands for N equals 1, S tilde stands for L equals 0, like S wave, and sigma stands for m or lambda equals 0. So now we can move to the two-electron diatomic system, where the Hamiltonian is now can be split in three parts: the Hamiltonian of electron 1, electron 2, and now we have this term of interaction. So each one of these two is already solved before, and we have eigenstates characterized by the three quantum numbers. So this is done, as explained in the previous slides. That's why it is in bold here. What is still unknown is this electron-electron correlation term. So we have seen in the spherical case, few slides before, that this term can be developed on the Legendre polynomials. This is in spherical coordinates. In prolate spheroidal coordinates or elliptic coordinates, an equivalent development exists due to von Neumann, and it looks like that. So at first look, it seems quite complicated, but if you look at it again, like here, and compare it with the spherical development, if you expand the Legendre polynomial on the spherical harmonics, you start to see some analogy here, kind of double sum on L and M, a kind of term here, combinatory term dealing with quantum numbers. We have something much simpler here, but still. And then the harmonic, the spherical harmonics are replaced by equivalent kind of elliptic harmonics, while the radial terms are replaced by the first kind and the second kind associate Legendre functions, which are tabulated, and you can code them quite easily. It is here nice to see that in the asymptotic regime, where electron is very far from the core, the mathematic rigorous expansions of both functions are xi to the power L, very analogous to r to the power L here in the upper part of the fraction, and 1 over xi to the power L plus 1, exactly this one. So this allows you to see that this analogy is between the diatomic system and hydrogen atom is still possible. Next step, calculate and solve calculate the spectrum, so solve the Schrödinger equation. So in principle, it should be possible to proceed like in any ab initio calculation. Take a very large basis, build up a Hamiltonian, huge matrix, diagonalize it with a big computer, and come out with the energies. This is very costly and not very efficient, except for the lowest states, as you will see. An alternative is the R-matrix treatment, where the full configuration interaction calculation is performed only in a small part of the configuration space around the nuclei. This is the main idea. So if we accept the following assumption or limitation, is that only one electron can escape from this volume, which is more or less always possible, depending which range of energy you want to study. You can enlarge the box or the size of volume to be able to deal with that. And then use the R-matrix method in spherical coordinates or in elliptic coordinates. So the Halford R-matrix method is specifically based on the use of prolate coordinates, and the reaction volume is now not a sphere but an ellipsoid, where the nuclei A and B occupy the foci of this ellipsoid. The electron that can escape from this volume when it is quite far from the system. Let me remind you that the system I'm dealing with is two nuclei, say two protons, one inner electron and one outer electron. So with this, we have the H2 molecule. So the inner electron screens partially the two protons, giving an average like a half charge, positive charge, effective positive charge on each center. So half can be translated to half-ion system, and this is the name given to the system. So to summarize the half-ion method without going into the, I removed all the equations from this presentation, but if you need them, just send me an email and I will send you all the literature about that. So the half-ion models define a kind of fictive particle, here the half-ion particle with two fractional charges resulting from the screening of the inner electron of both charges here, which makes the comparison of H2, which is two electron system, directly with hydrogen atom more natural and separate correlation effects from long-range ones. And the method itself can be summarized as follows. Inside the given finite reaction volume, we treat the problem in its full scale, which means we solve the Schrödinger equation taking into account all the possible interactions under the assumption of Bohr-Oppenheimer approximation and non-relativistic quantum mechanics. Outside this volume, we make this assumption which simplifies the problem and allows for the calculation of the wave function of the outermost electron using the same quantum mechanics tools. Then combining both and matching the solutions at the surface here allows for summarizing all the information in a key quantity which can be translated in the kind of quantum defects. So we come back to very simple things, but here the quantum defects are in the form of kind of matrix having diagonal and off-diagonal elements, the dimension of which is in general very small, like 3 to 10, which is a huge reduction of the complexity of the problem given the infinite number of states in each channel. And thanks to that key quantities, we will be able to calculate the cross sections and the rates of the different processes I have listed at the beginning of the lecture, and to give them as an input to other codes dealing with the modeling of the fusion itself. So this is the whole idea behind this method. So if now I come back to the same slide listing the different processes, you have already seen this in different colors. Let me give you an example of application to two processes: the rotational excitation of a diatomic system, to be Hd+, and the dissociative recombination also of Hd+ or H2+. So this work was done in collaboration with my colleague Johan Schneider from Le Havre Normandy University in France. So the idea here is that there are two possibilities for the H2+ or Hd+ ion to dissociate after a collision with an electron. This dissociation goes through either direct mechanism or indirect mechanism. And the indirect mechanism involves the Rydberg states. And that's why the quantum defect theory and the quantum defects we calculate are so important. The output of a typical calculation using the half-ion code for a specific symmetry will give quantities like which we call quantum defects. So here you have, for instance, 2 as functions of the internuclear distance, the bond length, and the coupling, the off-diagonal terms for both systems, for both channels, sorry. With these quantities, we can move to another code that called stepwise MQDT code developed by Johann Schneider and collaborators. And we can calculate the cross sections and the rates for this specific mechanism. So as you can see here, for instance, I hope you can see clearly the graphs. So this is for the direct process, the cross section as function of the energy and logarithmic scale, basically a decreasing line here with some dips here for the S wave and the D wave. But when we add the indirect process, you see how complex these cross sections becomes and how these resonances, these very sharp resonances appear, and these are very important to compare with experimental results. Another example concerning the rotational excitation, collaboration with the same team. Here, what is plotted is the rate coefficients as function of the electronic temperature, so or kinetic energies, and kelvins. You see here the low energies, low temperatures below 1000 Kelvin, and the different curves in different colors corresponds to different rotational excitation of the ion, starting from the fundamental excitation level with the specific quantum number for rotation ni plus equals 0, then 1, etc., up to 10. So the previous studies were considering only the lowest rotational states, and here we have demonstrated that taking into account higher rotational states, especially here, which was unexpected, can really contribute even by 2 orders of magnitude in the increasing of the reaction rates. Okay. There are so many other examples, but I will limit myself to this example before going now in the remaining part of the lecture to address another question. The Halfram-R matrix method is one of the theoretical available methods to calculate the ingredient for the calculation of cross sections and rate coefficients for the atomic and molecular processes, so that they can be used themselves as input to more large modeling systems of the plasma itself, including hydrodynamic physics, etc. Okay, this is good. And many other methods and codes exist all over the world. One key question is rising now, and it is of big importance for the community, and was recently discussed in the IAEA, is the assessment of the accuracy and the quality of calculation. Probably many of you are using their own research and their specific theme of research, some code that takes some input. They run the code for minutes, hours, days, weeks, or more. And then the codes deliver output numbers depending on what you are calculating, like energies, on whatever any quantum mechanical observable you can think about. The question is, how accurate is, or how accurate are your data? How can you assess them? How can you make sure that they are good enough to be reliable and can be used for other calculations? This is very important in all the fields, I guess, of physics. But it can be even more important here because, as you have seen, there are several stages, kind of ab initio, early stage calculation gives the properties of the processes. These properties are then injected in other codes to calculate like cross sections and rates of specific reactions, the output of which is used to feed other codes to model the fusion. So it is important to be sure at every step that the accuracy is good enough. So in our case, in the Halphium code, a good test is the spectroscopy. Spectroscopy can be very accurate and very precise. So if you compare your energies with the spectroscopic results, this is a good assessment. And we have shown that we can have less than one wave number accuracy in some case. Beyond that, in the few remaining minutes here, I'm looking at the time. We are proposing a kind of very simple recipe to assess the ab initio calculations, which are similar to those we are doing. So for instance, you need, let's say, some potential energy curves of a given molecule, H2, in some symmetry. What you do is you look at the literature and you find these kind of tables giving, for instance, for different values of internuclear distance, the energies of some states. In a table like that, you cannot see anything. I'm just displaying it to show you how difficult can be the task of saying yes or not if these numbers are accurate by the eye or not. There is no way to know that. So how to assess their accuracy? If we take, I make a zoom, I take an example here for a given symmetry, for some values of R in atomic units, and the 12 first roots published in this example. Here, once again, for a given distance, let's say 2 atomic units, you have numbers, all of them are negative, all of them are below the ionization threshold. So you cannot say if they are good or not, and you can think that they are good enough. In any case, I think this was the feeling of the authors as they decided to publish their results in this very good journal. So now, using our formalism based on quantum defect theory, converting these energies into quantum defects or quantum effective quantum number, we can assess them and say the following. As we expect that the quantum defect should remain almost constant. It is the case here for the states in green, as you can see, but no more the case for the other ones, especially this one. You can clearly see that it is totally out of scope. So if we draw that, if we plot the quantum defects as function of the principal quantum number, you can see that for the 5 first ones, it's okay, it's almost constant, and then it is completely different. While our calculations using our code gives, as expected, the good behavior. So we can repeat this operation for time is running, so I'm going to go fast to allow for a few questions, if any. So we can repeat this procedure and at the end of the day give a diagnostic in this kind of traffic light: green for good, orange for not that good, and red for absolutely bad results, cannot be reliable, and any calculation using these states for further purpose is not at all recommended. So unfortunately, we found several examples on the literature, not only that one, but others, including not only bound states, but also doubly excited states, what we call here sigma minus states. We have calculated ourselves a few years ago, and we found the same kind of discrepancy, not only in H2, but also in other systems like helium H+ system, where you find a huge gap, like a fraction of an EV, which is very large at this scale of energy. But still, it was published because it's not possible for the journals and the referees to check everything. So the goal here is not just to mention that for some publications there are bad results. This cannot be a goal by itself, but just to draw the attention of the community that there are simple recipes they can use before deciding whether their results are suitable for publication or not. And this recipe is just convert the energies in quantum defects, and they will immediately see if it is good or not. Of course, there are also very good examples here. I'm citing quite recent results of ab initio calculations, which are very good. Why are they very good? Because, of course, of the quality of the work and the codes and everything was done very carefully, but also thanks to the fact that they limited themselves to the lowest states, as you can see here, 5 or 6 potential energy curves, the energy versus the internuclear distance. If they tried like the others to go to higher energy, they would face problems. So the message here is that there are simple recipes you can use. Okay, now I still have 3 minutes, so I am going to conclude, if you allow me for. First, by saying that the atomic and molecular processes play an important role in fusion-edge plasma, and they impact their properties and behavior. Among these processes, the electron-molecule collisions is a challenging problem, especially at low energy. It is important for modeling physics. Among the most successful theoretical frameworks, the one combining our matrix theory and quantum defect theory looks very nice, especially for 2 electron molecules, and can also serve as a method to assess the uncertainty of the results, which is very, very simple. Okay, I am done. Thank you very much.
Thank you so much, Dr. Mourad, for the presentation. Can we open the floor for questions? Do we have any questions? Okay, so actually, I do have some few questions, if you allow me. First of all, you've mentioned that there's the intermediate molecule. You start with the initial state and you go to the intermediate molecule first. So I do not understand. We use usually some kind of approximation, perturbation theory or something like Fermi golden rule to go from from initial to final state. So how useful is the intermediate state? Why should I be interested in studying it?
Yes, thank you for this question. So actually, maybe I was not clear enough on that. Apologies. What I mean by intermediate state is not one of the states of the system, is not one of the quantum states of the system. What I mean by the intermediate system or a compound is that, imagine the following situation. You have a diatomic ion. Okay, here we are. So you do you see the slide?
Yes, I can see it.
Okay, nice. So you have H2 plus as a target, and an electron is colliding on it.
Okay.
Eventually, the system will be excited or dissociated or whatever. But for a very brief period of time, which can be quantized, it's kind of lifetime, the two components here, the electron and H2 plus, form a neutral molecule. This is what I'm calling an intermediate state. So actually, it's not an intermediate state, it's an intermediate compound. So the electron recombine with the ion to form a neutral, but the neutral has a lot of energy, enough energy to either ionize again or dissociate. So this is what I'm meaning by the intermediate compound and not the quantum state.
Okay, so we essentially ignore the subsequent interactions, and we consider that's a final state in itself, that intermediate molecule, right?
It turns out that the accurate description of this compound state is really crucial. This is the hardest part. So that's why when you are in the high energy regime, doesn't matter, because the electrons are fast enough to immediately dissociate the molecule, so you do not need it. But at low energy, the probability or the cross-section of electron capture is high enough that you form this compound, and you can have time for internal energy conversion, which gives birth to different channels. So that's why, how to say it, in this case, it is really crucial. It is very important. You cannot ignore it at all. You have to describe it accurately. Otherwise, the cross sections and the rates you obtain at the end of the day are not reliable at all.
Okay, so it's still a metastable, if we can say that. It's
yes,
but you need to understand it's
yes. You can see it like a kind of metastable state with the kind of lifetime. Absolutely.
Okay, so I have another question. When we are solving this, we are basically solving this very complicated Schrödinger equation, right?
Yes.
And we do some approximations, and we end up, I mean, from the high energy or low energy regime, and we end up with something like the R matrix technique to solve the problem numerically. So my question is, why not just apply that technique without using any approximations? Is that much more computationally hectic, or is there a reason why the approximations are?
Yes, of course. Yeah, of course. Ideally, what we would like to have enhanced is a tool, theoretical tool and numerical tool that can solve exactly the problem we are dealing with. But the complexity of the problem is so high that if you don't make any reasonable approximation, like Born-Oppenheimer approximation or the what I call the Halphium approximation, to obtain converged reliable results with the available computing resources we have now, it will take a huge amount of time. And by the way, if I can just make a comment, you have had lectures by Professor Ahmed Yunus about quantum computing, and this theme is under development, specifically because there are problems like this one, which even with exhausting all the possible computing resources available today, we cannot solve the exact problem within a reasonable finite time. So we do need approximations, as always in physics. The challenge is to make the good choice of these approximations, so that the approximate problem you are solving and the approximate solutions you are finding are close enough to the exact ones, so that the calculation makes sense and you can use them in practice.
Okay, but these calculations essentially are they global technique, or should they be studied case by case depending on the molecule and so on? Like, can I use the Halphium for whatever molecular processes, or is it only useful in some certain cases?
Yes, to be specific for the Halphium R matrix method, it's very limited, actually, limited to diatomic case, but it's the relevant case in the physics we are dealing with. So it is, let's say, important
But still
within
the
this.
diatomic system, right?
Yes, but it is not universal, and there are unfortunately no universal method that works for in every case. The theory, of course, I mean, the theory is there for more than a century. H psi equals E psi, if you like. Non-relativistic Schrödinger equation is there.
Sure.
So if you have a Hamiltonian, just solve the Hamiltonian and you have the solution. This seems very simple on the paper, but to implement it in real case and have significant figures and the results which compare with experiment, it's very hard.
Okay, so one last question, if I may. you've mentioned the quantum defect analysis as a some kind of a double check to the results and comparing them to see the uncertainty. Should that be done by the peer review or the researcher himself?
Can you repeat the last part, please? I didn't hear the last word.
Should this analysis be checked by the researcher himself, or should it be the responsibility of the peer reviewer to double check it and make sure that there's no bad results coming from the?
Yeah, it can be done by both, but my recommendation would be that it should be done by the researcher himself prior to the publication. I'm sure that you see here in the slide I'm displaying now.
Yes.
In this example, the energies, if you like, just to go a little bit into details, why these 12 routes only are published? Because what they do, they build up a huge Hamiltonian matrix. It can be tens of thousands or even larger matrix, diagonalize it, and say that the lower roots, the lowest or the lower roots should be converged. So how to decide if only the 3 first or the 5 or the 20 first are converged? One of the tests they do in general, they compare to the ionization energy. So if the energy of the root is lower than that of lower than the limit, it means that's a bound state. So it's okay. So as you can see here, even the last one is below the ion. So for the researcher, it's okay. But still, in this case, it's not converged, and he cannot see this problem just looking at the energies themselves. If he convert it in quantum effective quantum numbers or quantum defects, he would have seen it immediately. And in my opinion, he would certainly decided to not to publish these ones and do like the good examples I have shown at the end, the very accurate and good results recently published. They restrict themselves to the lowest states, so they are sure about the quality and the accuracy of their results.
Okay, so I thank you so much. We'll have to end it. Sorry for going over time with this.
Thank you.
Thank you so much, Dr. Mourad. We look forward to meeting you again.
Thank you very much, and greetings once again to everyone present here in the lecture.
Thank you. Goodbye.
Bye.